Welcome to Sleepy Science Stories. I'm so glad you're here. Before we begin, I'm curious, where are you watching this from? And what time is it where you are? Whether you're tucked in bed as the day winds down, or perhaps it's the middle of the night and sleep eludes you, you're exactly where you need to be. Tonight's journey will take us through the gentle realm of science and wonder. No rushing, no urgency, just a slow, peaceful exploration designed to ease your mind and guide you toward rest. So find your most comfortable position. Let your body sink into wherever you're resting. Take a slow, deep breath, and another. Tonight, we explore one of Earth's most fundamental mysteries, a question so simple that children ask it on beach vacations, yet so profound that it connects geology, chemistry, biology, and the very formation of our planet. We're going to discover why the ocean is salty. Not just salty, but precisely salty in a way that has remained remarkably stable for hundreds of millions of years. Picture yourself standing at the edge of the sea. Perhaps you've done this before. Toes sinking into wet sand, the rhythm of waves approaching and retreating, The air tastes of salt. If a wave splashes high enough to mist your face, you taste it there too. Sharp, mineral, unmistakable. That taste is so familiar to anyone who's visited the coast that we rarely stop to wonder about it. But tonight, we will wonder. We'll wonder deeply and slowly, following the story of salt from the birth of oceans billions of years ago to this present moment. The ocean's saltiness isn't an accident. It's the result of processes so patient, so gradual, that they make human lifetimes seem like quick heartbeats. Rivers flowing, rocks dissolving, minerals accumulating, all happening at a pace so leisurely that you could watch for your entire life and see no change at all. And yet, over the vast stretches of geological time, these gentle processes have transformed Earth's water into something unique in our solar system. A massive, stable solution of dissolved minerals that covers most of our planet's surface. You might wonder why we don't simply say, the ocean is salty because salt is in it. That would be true, but incomplete, like saying a book is words or a symphony is notes. The ocean's chemistry is a story, and like all good stories, it has a beginning, a middle, and a continuing present that shapes everything living in and around the sea. If you could travel back to the earliest oceans on Earth, before life, before continents, as we know them, you would find water that tasted quite different. Those ancient seas were not sweet. They were acidic, aggressive, hungry to dissolve the rocks that formed the young ocean floor. Over time, through processes we'll explore gently and thoroughly tonight, those fierce waters mellowed. They filled with minerals dissolved from the land and the seafloor itself. Sodium and chloride came to dominate. The familiar table salt we know, but they're accompanied by a supporting cast of other ions that together create the ocean's complex chemistry. The taste of seawater is relatively uniform across the world's oceans, despite their vast size. Dip a cup into the Atlantic off the coast of Maine, and another into the Pacific near Australia, and the salt concentration will be remarkably similar. This uniformity itself is worth contemplating. The oceans are not separate bowls but a single, connected body of water, stirred by currents that loop around the globe, mixing surface and deep waters in patterns that take centuries to complete. This mixing ensures that salt from rivers in China eventually spreads throughout the world ocean, just as minerals washed from the Andes find their way into every sea. There's something almost meditative about this. The ocean's chemistry is a global average, a planetary equilibrium reached through millions of years of dissolution and deposition, evaporation and precipitation, geological activity and biological intervention. And through it all, the concentration of salt has remained stable enough that life could evolve to depend on it. Organisms could calibrate their internal chemistry to match it, and ecosystems could build themselves around this salty foundation. Perhaps you've tasted seawater accidentally while swimming. It's a taste that lingers, more intense than you expected. That single swallow contains sodium and chloride, certainly, but also magnesium, calcium, potassium, sulfate, and traces of nearly every element on the periodic table. The ocean is not merely salty water. It's a dilute solution of almost everything Earth has to offer, a liquid library of the planet's chemistry. As we begin this exploration, let your breath settle into a rhythm like the waves, in and out, slow and steady. The story we're about to tell has no urgency to it. Salt has been accumulating in the oceans for billions of years. A few hours to understand the process is time well spent, time without pressure or deadline. Each chapter will deepen your understanding gently, building on what came before without rushing toward what comes next. The ocean has always been salty, for as long as there have been true oceans, but the level of saltiness has varied, the specific chemistry has evolved, and the sources of salt have changed as the Earth itself has transformed. Continental drift, the rise of life, the emergence of land, plants, volcanic activity, all these have played their role in making the ocean what it is today. And somehow, despite all this change, the ocean has maintained a relatively stable salinity that allows life to thrive. Before we dive deeper into the mechanisms, the rivers and rocks, the chemistry and circulation, let's simply appreciate the mystery. Why should Earth have salty oceans at all? Mars doesn't. Venus doesn't. The ice moons of Jupiter might have subsurface oceans, but their chemistry remains unknown. Our ocean's saltiness is part of what makes Earth, Earth. It's a signature of our planet's activity, its dynamic geology, its water cycle, and the intricate dance between land and sea that has persisted since water first condensed from the atmosphere billions of years ago. So tonight, as you relax into this exploration, remember that you're learning about something fundamental. The salt in the sea connects to the mountains being worn away by rain, to volcanic vents at the bottom of the ocean, to the clouds forming and releasing fresh water in an endless cycle. It connects to life itself, because the chemistry of our own blood echoes the chemistry of ancient seas. We carry a memory of the ocean inside us, a subtle saltiness that speaks to our origins. Let the waves continue their rhythm in your mind. Let the questions arise without demanding immediate answers. We have time tonight, all the time we need. The story of the ocean's salt is patient, and so are we. Chapter 2: When Water Came to Earth. To understand why the ocean is salty, we must first understand how Earth came to have oceans at all. This takes us back to the very beginning, to a time so remote that it barely seems real, and yet it happened, as surely as the ground beneath you exists now. 4.5 billion years ago, our solar system was forming from a vast cloud of gas and dust. gravity pulled this material together, creating the sun at the center and allowing smaller clumps to orbit around it. These clumps collided, merged, grew larger. One of these growing bodies would become Earth. In its earliest form, our planet was nothing like the blue marble we know today. It was a hellish place, a molten sphere perpetually bombarded by asteroids and comets. Its surface glowing red with heat, any water that arrived immediately vaporizing into steam. You might picture Earth at this stage as a ball of liquid rock, so hot that mountains and valleys couldn't exist because the entire surface flowed like thick honey. The temperature was high enough to melt iron and stone alike. If you could have visited, though you'd need more than a very good time machine, you'd need resistance to heat that no material possesses. You would have found a world beneath a thick atmosphere of steam, carbon dioxide, and nitrogen, with no solid ground to stand on. But even in this inferno, water was present, trapped as vapor in the crushing atmosphere. Some of this water had been part of the original dust and rock that formed Earth, locked into minerals as they condensed from the solar nebula. More arrived with every comet that struck the surface. Icy bodies from the outer solar system, delivering their frozen loads that immediately became steam on contact. Time passed, millions of years. The bombardment gradually lessened as the inner solar system cleared of debris. Earth's rotation slowly stabilized. Heat radiated away into the coldness of space, gradually, so slowly that it would have been imperceptible to any observer. The surface began to cool. The molten rock started to solidify into a thin crust, a fragile skin over the still liquid interior. And then, perhaps around 4 billion years ago, something extraordinary happened. The surface cooled enough that water could exist as a liquid. The thick atmosphere, saturated with steam, began to rain. Imagine this rain. Not the gentle showers you know, not the thunderstorms of summer afternoons. This was rain on a planetary scale. A deluge that lasted for millions of years. Rain falling on rock so hot that it immediately flashed back to steam. But gradually, infinitesimally, cooling that rock through the transfer of heat. Rain filling the first depressions in the cooling crust, creating puddles that grew into pools, pools that merged into lakes, lakes that expanded into seas. The early ocean was born from this long, patient rain. There was no gradual accumulation of water in river valleys and ocean basins. Instead, water fell from the sky for eons, accumulating everywhere the topography allowed. The atmosphere, once thick with steam, gradually cleared as its moisture condensed and fell. The sky, which had been perpetually clouded, began to reveal the stars. This water that fell to form the first oceans was not pure. It had been part of an atmosphere rich in volcanic gases, carbon dioxide, sulfur dioxide, hydrogen chloride. These gases dissolved in the rain, making it acidic. The first rainwater to touch the cooling crust was more like dilute acid than the fresh water you know from mountain streams. This acidic water was hungry, chemically aggressive, ready to react with the rocks it touched. Consider the surface of the young Earth beneath this acidic rain. The rocks were primarily basaltic, similar to the dark volcanic rocks you might find in Hawaii today. These rocks contained sodium, calcium, magnesium, iron, and many other elements locked in mineral structures. When acidic water touched these minerals, chemical reactions began. The acid donated hydrogen ions to the rock minerals, and in exchange, the rocks released other ions: sodium, calcium, magnesium, chloride, into the water from the very first moment of its existence. Then, the ocean was beginning to dissolve the earth itself. This dissolution was slow, gentle, but inexorable. Every raindrop that fell, every wave that lapped against rock, every current that flowed across the seafloor participated in this chemical exchange. The ocean was becoming a solution, in the precise chemical sense of the word, a liquid in which many substances were dissolved. The early ocean was smaller than today's ocean. The continents as we know them did not yet exist. Instead, the surface was probably covered by numerous volcanic islands and vast stretches of oceanic crust, with water filling the lower areas. The ocean basins were shallower, the chemistry different in its details, but the fundamental processes were the same ones that continue today: water dissolving, rock carrying away ions, becoming salty in the process. At this point in Earth's history, the ocean's salinity was still changing rapidly. More rain fell, adding more fresh water and diluting the dissolved minerals. But at the same time, more minerals were dissolving from the rocks. Volcanic activity was intense. The young Earth was still cooling, still geologically violent. Underwater volcanoes released dissolved minerals directly into the sea. Hydrothermal vents opened where seawater seeped into cracks in the hot seafloor, heated up, dissolved minerals from the surrounding rock, and then erupted back into the ocean as hot, mineral-rich fluid. You might wonder if the ocean tasted salty yet. Probably not in the way it does today. The balance of ions was different, with more calcium and magnesium relative to sodium and chloride. The pH was likely more acidic than the modern ocean's mildly alkaline chemistry, but the ocean was definitely acquiring a mineral taste, becoming something other than pure water. Life may have emerged in these early oceans, though exactly when remains uncertain. The first organisms would have been microscopic, simple, adapted to high temperatures and unusual chemistry. These early life forms began to influence ocean chemistry themselves, removing certain elements for their biological needs and releasing others as waste products. Even at this early stage, life and ocean chemistry were beginning their long, intertwined dance. As millions of years became hundreds of millions, the ocean deepened. Water continued to arrive from the interior of the Earth, released by volcanic outgassing. The water cycle established itself: evaporation, condensation, precipitation. Rain fell on the emerging volcanic islands and the first protocontinents, forming streams and rivers that carried dissolved minerals to the sea. These rivers were delivering sodium, chloride, and other ions continuously, constantly replenishing what the ocean had dissolved. The ocean's chemistry began to stabilize, finding a rough equilibrium between the minerals being added and those being removed by geological and biological processes. The concentration of salt increased toward something more recognizable, though still not identical to today's ocean. The water became denser as it filled with dissolved ions. Its freezing point lowered, its boiling point rose. It became harder for the sun to evaporate it, because lifting water molecules away from a solution takes more energy than evaporating pure water. By about 3.5 billion years ago, the Earth had a substantial ocean, a salty ocean, though not yet quite as salty as today. This ocean covered most of the planet. Life was evolving within it, beginning the long process that would eventually lead to stromatolites, algae, fish, and all the marine diversity we know. And through it all, rivers kept flowing to the centered sea, carrying their dissolved loads of minerals, perpetually replenishing the salt. Let your mind rest with this image. The young earth beneath a clearing sky, an ocean forming from ancient rain, rocks dissolving slowly into water, the first ocean becoming salty through patient chemistry that needed no intelligence, no design, just time and water and stone. The process that made the ocean salty began as soon as water could exist in liquid form, and in a real sense, it has never stopped. The ocean is still dissolving the earth. Rivers are still delivering minerals to the sea. The same processes that created the salt content of the early ocean continue today, refining and maintaining the chemistry we know now. Chapter 3. The rain that never stopped. Rain has been falling on Earth for 4 billion years. This simple fact is worth dwelling on, allowing it to sink in slowly, like water into soil. 4 billion years of rain. Not every day, not everywhere at once, but somewhere, always. Water vapor condensing into droplets, falling through the atmosphere, striking the surface, gathering into streams, flowing toward the ocean. Each raindrop begins its journey as pure water, or nearly pure. As water evaporates from the ocean, it leaves behind the salt and other minerals. The vapor rises into the atmosphere carrying only water molecules. This is nature's distillation process, played out on a planetary scale. The sun provides the energy, lifting trillions upon trillions of water molecules from the ocean surface every day, transforming liquid into gas, leaving everything dissolved behind. High in the atmosphere, this water vapor cools. Molecules cluster together around tiny particles of dust or salt crystal, forming droplets. These droplets combine, grow heavier, and eventually fall. And as they fall through the atmosphere, they begin to collect other substances. Carbon dioxide dissolves into the droplets, forming a weak carbonic acid. Other gases dissolve as well. By the time rain reaches the ground, it is already slightly acidic, mildly reactive, capable of dissolving minerals from whatever it touches. Imagine a single raindrop falling somewhere over a mountain range. Let's follow its journey. It strikes bare rock high on a slope, granite perhaps, or basalt, or limestone. The drop splashes, clings to the surface for a moment, then slides down the rock face, joining other drops to form a tiny rivulet. And in that brief contact with rock, the water begins to work. The mild acidity reacts with minerals in the stone. Incredibly small amounts of material dissolve. Sodium ions, calcium ions, chloride, bicarbonate, amounts so tiny that a million raindrops might dissolve only a grain of sand's worth of material. But multiply this by every raindrop, every surface, every moment, over millions of years. The rivulet becomes a stream, trickling downslope. It flows over more rock, through soil where the water contacts countless mineral grains, roots, decomposing organic matter. More material dissolves. The water becomes a very dilute solution of many substances. Sodium, potassium, calcium, magnesium, chloride, sulfate, bicarbonate, all present in concentrations so low that the water still tastes fresh, looks clear, appears pure to the eye. But chemically, it is no longer pure H2O. It has become a mineral transport system. This stream joins others, forming a creek. The creek descends through a valley, sometimes flowing over hard bedrock, sometimes through accumulated sediments. Different rocks yield different ions. Limestone readily releases calcium and bicarbonate. Halite deposits, if the water encounters them, contribute sodium and chloride directly. Granite yields sodium and potassium more readily than calcium. The specific chemistry of the stream depends on what rocks it flows across. But in every case, water is dissolving the land. The creek becomes a river. Now the water carries not just dissolved ions but also sediment, particles of rock and soil suspended in the flow. These particles continue to release ions as they travel, their surfaces in constant contact with water. The river winds across the landscape, sometimes fast, sometimes slow. In some places, it cuts through rock, actively eroding and deepening its channel. In other places, it spreads across floodplains, depositing sediment during floods and picking it up again when the water recedes. And always, every day, every hour, the river is carrying dissolved minerals toward the ocean. The concentration is low. River water typically contains only a few hundred parts per million of dissolved solids, compared to the ocean's 35,000 parts per million. You can drink river water without tasting salt, but those dissolved ions are there, invisible, making their patient way to the sea. When the river finally reaches the ocean, the fresh water mixes with salt water. The dissolved minerals the river has carried, the sodium extracted from feldspars, the calcium released from limestone, the chloride weathered from ancient evaporite deposits, join the vast inventory of ions already dissolved in the sea. The river's contribution is vanishingly small compared to the ocean's total volume, but the river is one of thousands, and each has been flowing for millions of years. Consider the Amazon River, the world's largest by volume. It delivers about 200,000 cubic meters of fresh water to the Atlantic Ocean every second. Within this flow are dissolved minerals, roughly 100 million kilograms of sodium and chloride every day, along with substantial amounts of calcium, magnesium, potassium, and other elements. This is just one river. The Mississippi, the Congo, the Yangtze, the Ganges, each contributes its own load of dissolved minerals. Smaller rivers contribute less individually, but there are millions of them. Scientists estimate that rivers collectively deliver about 3 to 4 billion tons of dissolved minerals to the oceans every year. This sounds like an enormous amount, and over geological time, it is. 3 billion tons per year, sustained for even 1 million years, yields 3 quintillion tons of dissolved material. The ocean contains about 50 quintillion tons of dissolved minerals, which means that at current rates, rivers could account for the ocean's entire salt content in something like 15 to 20 million years. But the ocean is at least hundreds of millions of years old, more like billions, which means there's something else going on. The ocean should be much saltier than it is if rivers have been pouring minerals into it for billions of years with nothing removing those minerals. We'll explore this mystery of balance later in our journey tonight. For now, simply appreciate that rivers are incredibly effective delivery systems for salt, moving minerals from land to sea with patient persistence. You might picture the water cycle as a circular process. Ocean to atmosphere, to rain, to rivers, to ocean. But it's not a perfect circle. Each time around, some minerals are added to the ocean. The water evaporates again. pure, leaving those minerals behind. It's a ratchet system, a one-way valve for salt. Water goes round and round, but salt accumulates in the sea. The rain that dissolved minerals from the young Earth's surface billions of years ago is, in a real sense, the same rain that falls today. The water molecules themselves have been recycled through the water cycle countless times. But each cycle, they participate in the slow dissolution of continents, the gradual transfer of the solid earth into the liquid ocean. Rain carves valleys, crumbles mountains, turns rock into sediment, and sediment into ions dissolved in water. Over tens of millions of years, entire mountain ranges can be worn away, grain by grain, ion by ion, delivered to the ocean by rivers that never tire. There's a certain poetry to this. The ocean has been made salty by the destruction of the land. Every sodium ion in the sea was once locked in rock on a continent. Every chloride ion was either released from ancient salt deposits or emerged from volcanic activity. The ocean is, in a sense, made of dissolved continents, a liquid archive of Earth's geological history, a solution that remembers every mountain that ever eroded away. Let your mind rest with the rain. Hear it falling somewhere, anywhere, right now, on forests, on deserts, on glaciers and grasslands and bare stone, each drop doing its microscopic work, releasing a few ions here, a few there, contributing to the flow that feeds the rivers, which feed the sea. This has been happening since before there were forests, since before there was life on land at all. And it continues now, as patient and steady as the rotation of the earth itself. Chapter 4. Rivers as chemical highways. Rivers are not merely channels for water. They are chemical highways, transportation networks, that move dissolved minerals from the continents to the oceans with remarkable efficiency and endless persistence. Every river on Earth participates in this transport, from the greatest to the smallest, from the Amazon to unnamed creeks flowing through remote wilderness. The chemistry of river water varies enormously depending on what rocks the water has flowed across. A river draining volcanic terrain will have a different chemical signature than one flowing through limestone country or ancient granite. Yet all rivers share certain characteristics. They are dilute solutions, containing far less dissolved material than seawater, and they all flow in one direction, downhill, toward the sea. Let's follow a river system from its headwaters to its mouth, watching what happens to its chemistry along the way. High in the mountains, snowmelt and rain collect in tiny streams. This water is very pure, having had minimal contact with rock. It's cold, fast-flowing, tumbling over boulders in its rush downslope. But even here, dissolution is occurring. The water's slight acidity from dissolved carbon dioxide reacts with mineral surfaces. Sodium begins to leach from feldspar crystals. Calcium separates from limestone, where the stream crosses such rocks. As the stream descends, it gathers more water from tributaries. Its volume increases. Its flow sometimes slows as it enters gentler terrain. The water is in contact with rocks and soil for longer periods. More dissolution occurs. The concentration of ions increases, though it remains very low. If you tasted this water, it would seem perfectly fresh, with perhaps a slight mineral quality if you're paying close attention. In the middle reaches of the river, the chemistry begins to stabilize into a characteristic composition that depends on the river's drainage basin. Rivers flowing through limestone regions become rich in calcium and bicarbonate. Those draining basaltic rocks accumulate more sodium and magnesium. Rivers in regions with evaporite deposits, ancient dried-up seas that left salt layers behind, can carry significant amounts of sodium and chloride, even as fresh water. The river widens. Its flow becomes more complex, with different water masses mixing imperfectly. Deeper, slower water near the bottom may have slightly different chemistry than the faster surface flow. During flood season, the river may spread across its floodplain, picking up minerals from soils and rocks that are usually above water level. During dry season, the flow decreases, and the concentration of dissolved ions may actually increase because less water is diluting them. Throughout its length, the river is also transporting sediment, physical particles of rock and soil. These particles continue to react with water even as they're carried along. Clay minerals, with their high surface area, can release or absorb ions. Organic matter decomposes, contributing carbon dioxide and organic acids that enhance the water's ability to dissolve minerals. The river is a dynamic chemical system, constantly changing yet maintaining overall patterns. When the river approaches the ocean, interesting things begin to happen. The gradient decreases, the flow slows. The river may split into multiple channels in a delta. Sediment settles out as the current weakens, building the delta landward. The chemistry becomes more complex as fresh water begins to mix with salt water. This mixing zone, the estuary, is chemically fascinating. Fresh water is less dense than salt water, so it tends to float on top, flowing out over a wedge of salt water that intrudes upstream from the ocean. The boundary between these water masses is not sharp but gradual, a transitional zone where chemistry changes meter by meter. Some organisms thrive in this variable salinity environment. Others cannot tolerate it and remain either in the fully fresh or fully marine portions. At the mouth of the river, finally, the fresh water delivers its cargo of dissolved minerals to the ocean. The concentration gradient drives mixing. Ocean currents disperse the river water, carrying its dissolved ions into the vastness of the sea. The minerals the river has carried, perhaps from mountains hundreds or thousands of kilometers away, join the ocean's inventory. But rivers deliver more than just sodium and chloride. Though these are the most abundant ions, they also carry calcium, which marine organisms use to build shells and skeletons. They deliver silica, which diatoms use to construct their intricate glass-like frustules. They provide iron, an essential nutrient for phytoplankton. In this sense, rivers are not just making the ocean salty, they're providing the raw materials that marine life needs. Different rivers contribute different balances of ions. The Mississippi River, draining much of North America, carries large amounts of calcium and bicarbonate from the limestone-rich regions of its basin. The Amazon, flowing through tropical South America, delivers water that has interacted with highly weathered soils and ancient rocks. The Ganges carries sediment and dissolved minerals eroded from the young, tectonically active Himalayas. Each river has its own chemical fingerprint. Scientists can measure the chemical output of major rivers quite precisely. They sample water regularly, measure ion concentrations, calculate the water discharge, and multiply these values to determine how much of each element the river is delivering to the ocean. When these calculations are summed up across all the world's rivers, the total is impressive: approximately 4 billion tons of dissolved material per year. You might visualize this as a global conveyor belt. Rain falls on continents, dissolves minerals, flows to the sea. The ocean receives this constant input of dissolved ions. Evaporation returns water to the atmosphere but leaves the ions behind. The cycle continues. Year after year, century after century, always transferring material from land to sea. The importance of rivers in ocean chemistry cannot be overstated. Without rivers, the ocean would be far less salty than it is. The continuous delivery of dissolved minerals, sustained over geological time, is the primary reason seawater tastes the way it does. Rivers are doing now what they have been doing for billions of years, dismantling the continents grain by grain, ion by ion, and delivering the products to the sea. Consider how patient this process is. A single sodium ion, released from a feldspar crystal in a mountain stream, might take days or weeks to travel downstream to the ocean. Once there, it becomes one among countless identical ions, indistinguishable from sodium delivered by other rivers or released from the seafloor. It will remain in the ocean for millions of years on average, circulating with the ocean currents until eventually it is removed by some chemical or geological process, incorporated into clay minerals, taken up by evaporite formation, or subducted back into the Earth's interior at a tectonic boundary. Rivers also vary in their flow over time, which affects their delivery of dissolved minerals. During wet seasons or after major storms, river flow increases dramatically. The water may become cloudy with suspended sediment, but its concentration of dissolved ions actually decreases because of dilution. During dry seasons, flow decreases, and dissolved ion concentrations can rise even as the total amount delivered decreases. Over very long timescales, rivers themselves change. Tectonic activity uplifts new mountains, creating new drainage patterns. Climate shifts alter precipitation patterns, changing which rivers flow strongly and which diminish. Ice ages lock up vast amounts of water in ice sheets, reducing river flow globally. When the ice melts, river discharge increases dramatically. Through all these changes, the fundamental process continues. Water flowing downhill, dissolving minerals, delivering them to the sea. Let your thoughts flow like a river, moving from one idea to the next without rushing, without turbulence. Rivers teach us about patience and persistence. They do not hurry, yet they accomplish enormous work over time. They are strong enough to carve canyons, but gentle enough to sustain life throughout their length. And they connect the highest peaks to the deepest oceans, making the Earth's chemistry whole. Chapter 5: How Rock Becomes Salt. The minerals dissolved in seawater did not begin their existence as dissolved ions. They were locked in solid rock, part of crystal structures, chemically bound, stable, and inert. Understanding how these minerals transition from solid to dissolved form is central to understanding why the ocean is salty. It's a story of water's remarkable power as a solvent, of chemical bonds breaking and reforming, of time measured in geological ages. Rock weathering is the process that releases minerals into this remains, water. It occurs everywhere rock is exposed to air and water, on mountaintops, in deserts, along riverbanks, and on the ocean floor itself. The mechanisms are varied, but they all involve water, directly or indirectly. Physical weathering breaks rock into smaller pieces without changing its chemistry. Frost wedging is perhaps the most dramatic example. Water seeps into cracks in rock. When temperature drops below freezing, the water becomes ice, and ice occupies more volume than liquid water. This expansion exerts tremendous pressure on the surrounding rock, widening the crack. Over many cycles of freezing and thawing, a crack becomes a fissure becomes a split, and eventually the rock breaks apart. The fragments expose fresh mineral surfaces to chemical attack. Temperature fluctuations alone can cause rock to crack, as different minerals expand and contract at different rates. Roots growing in rock crevices exert pressure as they expand, further fracturing the stone. Even the impact of blowing sand can abrade and fragment rock surfaces. All these physical processes increase the surface area of rock exposed to water, and surface area is crucial for chemical weathering. Chemical weathering is where ions actually dissolve into water. The most common and important process is called hydrolysis, literally, splitting by water. Water molecules are mildly polar, with a slight positive charge on the hydrogen end and a slight negative charge on the oxygen end. This polarity allows water to interact with many mineral structures, particularly those containing ions. Consider a common feldspar mineral, one of the most abundant minerals in Earth's crust. Feldspar contains sodium, aluminum, silicon, and oxygen, arranged in a complex crystal structure. When water contacts feldspar, especially acidic water containing dissolved carbon dioxide, a slow reaction begins. Hydrogen ions from the acidic water exchange places with sodium ions in the feldspar structure. The sodium ions, now freed from the crystal, are surrounded by water molecules and carried away in solution. The feldspar itself gradually transforms into clay minerals, which have a different structure than the original feldspar. This process is incredibly slow on human timescales. A single crystal of feldspar might take thousands of years to completely weather away. But on geological timescales, it's relentless and thorough. Given enough time, entire granite mountains, composed largely of feldspar and quartz, can be reduced to clay and dissolved ions. Different minerals weather at different rates. Halite, table salt, sodium chloride, dissolves readily in water with no chemical reaction needed. The ionic bonds holding sodium and chloride together in the crystal are easily broken by water molecules, which surround and separate the ions. This is why areas that were once ancient seabeds, where salt deposits formed from evaporated seawater, can contribute large amounts of sodium and chloride to rivers even millions of years after the seas dried up. Limestone, composed of calcium carbonate, weathers readily in acidic water. The reaction produces dissolved calcium and bicarbonate ions. Regions with extensive limestone bedrock often have rivers that are particularly rich in these ions. The famous cave systems found in limestone regions are created by this very process. Water slowly dissolving the rock, creating underground passages that can grow to enormous size over millions of years. Basaltic rocks, common in volcanic regions and making up most of the ocean floor, contain calcium, magnesium, and iron, along with silicon and aluminum. These minerals weather to release their components at different rates. Olivine, a common mineral in basalt, weathers relatively quickly, releasing magnesium and iron. Pyroxene releases calcium and magnesium. These ions join the water flowing over or through the rock. Biological processes accelerate chemical weathering. Plants and microorganisms produce organic acids as they grow and decompose. These acids, though weak, enhance water's ability to dissolve minerals. Lichens growing on bare rock surfaces actually speed up weathering significantly. Tree roots not only physically crack rock, but also release acids that promote chemical dissolution. The soil layer itself is an active chemical reactor where water, organic matter, minerals, and organisms interact in complex ways. The weathering of rock is also affected by climate. In warm, wet, tropical climates, chemical weathering proceeds rapidly. High temperatures speed up chemical reactions, and abundant rainfall provides plenty of water to carry out the dissolution. In cold, dry climates, weathering slows down. This is why ancient rocks can survive relatively unchanged in polar regions or high mountains, while similar rocks in the tropics weather away much faster. You might visualize the continents as slowly dissolving, though this happens far too gradually to ever witness directly. Every exposed rock surface is engaged in a chemical negotiation with the atmosphere and water. Carbon dioxide from the air dissolves in rainwater, making it mildly acidic. This acidic water contacts rock, reacting with minerals, releasing ions. Those ions are carried to streams, to rivers, to the ocean. Meanwhile, the rock left behind is slightly diminished, its structure altered, its surface roughened and etched. Soil formation is essentially rock weathering in action. Parent rock breaks down, both physically and chemically. The products, clay minerals, sand grains, dissolved ions, mix with organic matter to create soil. Plants grow in this soil, their roots penetrating deep, their metabolism affecting the local chemistry. When they die and decompose, they contribute organic acids and create pore spaces in the soil where water can penetrate. The soil layer becomes an efficient processor of rock material, accelerating weathering far beyond what would occur on bare rock surfaces. In mountains, where physical erosion is rapid due to steep slopes and active tectonics, fresh rock is constantly being exposed to weathering. The Himalayas, for instance, are rising due to the collision of India with Asia, but at the same time, they're being worn away by weathering and erosion. The rivers draining the Himalayas carry enormous loads of dissolved minerals and sediment. The rate of chemical weathering in this region is among the highest on Earth. The mountains rise, the rivers erode them, ions dissolve and flow to the sea, all parts of Earth's grand chemical and physical recycling system. At the ocean floor itself, weathering continues. Seawater circulates through cracks and porous regions of the oceanic crust. When this water encounters hot rock near volcanic regions, reactions accelerate. Minerals in the rock break down, releasing ions into the seawater. Some ions are added to the ocean this way. Others are removed from seawater by reaction with the rock. These hydrothermal systems, which we'll explore more deeply later, are another major pathway in the rock to salt transformation. The transformation of solid rock into dissolved ions is not instantaneous or simple. It involves multiple steps, many types of reactions, physical and chemical processes working together, but the overall pattern is clear. The solid earth gradually transfers material to the liquid ocean. Mountains become plains, become dissolved ions in seawater. It's a one-way flow over any timescale we can measure directly. Though on the longest geological timescales, there are recycling mechanisms that return some material from ocean to continent. Imagine a single atom of sodium, part of a feldspar crystal in a granite boulder high in a mountain range. Rain falls. becomes slightly acidic from atmospheric carbon dioxide. Over thousands of years, through countless wetting and drying cycles, freeze-thaw cycles, interactions with organic acids from pioneering lichens, the feldspar crystal begins to break down. The sodium atom's bonds to the crystal structure weaken, break, and finally, the atom finds itself surrounded by water molecules, carried into a microscopic water film on the rock surface. This film joins others, forms a droplet, then a rivulet. The sodium ion, now liberated, mobile, free, begins its journey downslope. It may take decades to reach a stream, but eventually it does. From there to the river, from the river to the ocean, and there it will remain, one sodium ion among an incomprehensibly large number of others for millions of years. Rock becomes salt through patient chemistry, through the persistent work of water and weather, through timescales that dwarf human civilization. And yet it's happening everywhere, all the time, including right now, as you rest and listen. Rain is falling somewhere. Minerals are dissolving. The slow transfer from stone to solution continues, as it has for billions of years, as it will for billions more. Chapter 6. The Chemistry of Salt Water. Seawater is not simple salt water. It's a complex chemical solution containing nearly every element found on Earth, though in varying concentrations. To truly understand why the ocean is salty, we need to understand what salty means in chemical terms and how this particular mixture came to be. When we taste seawater, what we're primarily tasting is sodium chloride, common table salt. These two ions, sodium and chloride, together account for about 85% of all dissolved material in seawater. Sodium makes up about 30.6 parts per thousand of seawater by weight. Chloride, about 19.4 parts per thousand. Together, they create that sharp, mineral taste we recognize instantly. But seawater also contains significant amounts of other ions. Sulfate is the third most abundant, at about 2.7 parts per thousand. Magnesium comes next, at about 1.3 parts per thousand. Calcium contributes about 400 parts per million. Potassium, about 380. These 6 ions, sodium, chloride, sulfate, magnesium, calcium, and potassium, make up more than 99% of the dissolved matter in seawater. Then, there are trace elements, present in far smaller amounts but still significant: bromide, fluoride, strontium, boron, silicon. Elements important for marine life despite their low concentrations: iron, nitrogen compounds, phosphorus, various trace metals, and truly trace elements, present in parts per billion or even parts per trillion: gold, uranium, rare earth elements. If you could extract and concentrate all the gold dissolved in Earth's oceans, you'd have about 10 billion tons of it, a staggering amount by human standards, though so diluted in the ocean's vast volume that extraction would never be economical. The total concentration of dissolved material in seawater averages about 35 parts per thousand, or 3.5%. This is usually expressed as a salinity of 35 practical salinity units. This means that if you evaporated a kilogram of seawater completely, you'd have about 35 grams of solid salts left behind. This concentration is high enough to prevent seawater from freezing until about -2 degrees Celsius. slightly below the freezing point of fresh water. It's high enough to make seawater noticeably denser than fresh water, about 3% denser, which is why it's easier to float in the ocean than in a freshwater lake. It's high enough to require special adaptations by organisms that live in the sea, because the salt water outside their bodies would draw water out of their tissues by osmosis if they didn't have mechanisms to counteract this. Yet it's low enough that the ocean remains liquid, flows freely, circulates globally. If seawater were much saltier, its properties would change dramatically. It would be denser, more viscous, harder for currents to circulate. Some marine organisms would reach the limits of their ability to regulate internal salt concentrations. The specific balance of ions in seawater is not arbitrary. It reflects the sources of these ions: the weathering of continental rocks, volcanic inputs, reactions with seafloor rocks, and the processes that remove them. Sodium and chloride remain in seawater for long periods, millions of years on average, because few processes remove them efficiently. This is why they dominate seawater chemistry. Chloride ions are particularly stable in seawater. They're chemically inert, not prone to reacting with other substances or being incorporated into minerals or biological structures. Chloride enters the ocean primarily through volcanic sources. Volcanic gases include hydrogen chloride, which dissolves in water to release chloride ions, and through the weathering of ancient evaporite deposits, beds of salt left by long-vanished seas. Sodium comes primarily from the weathering of silicate minerals in continental rocks. Feldspars, which are among the most common minerals in the crust, break down to release sodium. Once in the ocean, sodium is also quite stable. Some is removed by reactions with clay minerals, and some is trapped in evaporite deposits when seawater evaporates in enclosed basins. But most remains dissolved, circulating with the ocean currents. Magnesium and sulfate also come from rock weathering and volcanic sources. Magnesium is more reactive than sodium. Significant amounts are removed from seawater at hydrothermal vents, where hot seawater reacts with basaltic rock, incorporating magnesium into altered minerals. Sulfate can be removed by bacteria that reduce it to hydrogen sulfide in oxygen-poor sediments. Despite these removal mechanisms, both remain abundant in seawater. Calcium is interesting because its concentration in seawater is actively regulated by biology. Marine organisms, from microscopic coccolithophores to corals to shellfish, extract calcium from seawater to build shells and skeletons made of calcium carbonate. When these organisms die, their hard parts sink to the seafloor. In shallow or moderately deep water, calcium carbonate accumulates as sediment. In the deepest parts of the ocean, where pressure is high and temperature low, calcium carbonate dissolves. This biological cycle means calcium doesn't simply accumulate in seawater. Instead, organisms remove it almost as fast as rivers supply it. Silicon has a similar story. Rivers deliver silicon weathered from rocks. Diatoms, microscopic algae, use this silicon to construct their beautiful glass-like shells. When diatoms die, their silicon structures sink, accumulate on the seafloor, and eventually turn into rocks called chert or flint. Silicon concentrations in surface seawater are often very low because diatoms use it so efficiently. Deeper water contains more dissolved silicon because fewer diatoms live there. The chemical composition of seawater is also affected by biological processes that seem unrelated to salt chemistry. Photosynthesis by phytoplankton consumes carbon dioxide and releases oxygen. When these organisms die and decay, the reverse process occurs deeper in the ocean, consuming oxygen and releasing carbon dioxide. This creates vertical gradients in dissolved gases. Similar gradients exist for nutrients like nitrogen and phosphorus, which organisms take up in surface waters and release when they decay at depth. The pH of seawater, a measure of its acidity or alkalinity, averages about 8.1, which is mildly alkaline or basic. This pH is controlled by the carbonate system, a complex chemical equilibrium involving dissolved carbon dioxide, bicarbonate ions, and carbonate ions. This system buffers seawater against pH changes, keeping it relatively stable even as carbon dioxide dissolves in or out of the water. You might wonder if seawater everywhere has the same composition. The answer is nearly, but not exactly. The relative proportions of the major ions are remarkably consistent throughout the world ocean. Sodium is always about 55% of the total dissolved ions, chloride about 30%, and so on. This consistency exists because ocean currents mix water globally, homogenizing its chemistry over timescales of about 1,000 years. However, the total concentration, the salinity, does vary from place to place. Surface water in tropical regions where evaporation is high can have salinity of 37 or even 38 parts per thousand. Near river mouths, where fresh water dilutes seawater, salinity can drop well below 35. In enclosed seas, salinity can be much higher or lower than the global average. The Mediterranean Sea is saltier than the Atlantic because evaporation exceeds precipitation and river input in that region. The Baltic Sea is much less salty because it receives substantial river inflow and has limited connection to the open ocean. At the surface of the ocean, salinity changes with latitude. It's highest in the subtropics, around 20 to 30 degrees north and south of the equator, where dry air descends and evaporation exceeds precipitation. Salinity is lower near the equator, where rainfall is abundant, and lower at high latitudes, where precipitation exceeds evaporation and melting ice adds fresh water. With depth, salinity patterns become more stable. Deep ocean water has fairly uniform salinity, typically around 34.7 parts per thousand. This water is cold, having sunk from the surface in polar regions where cooling made it dense enough to descend. It carries the salinity characteristics of those cold surface waters into the deep ocean, where it circulates slowly, taking centuries to return to the surface. The chemistry of seawater represents a balance. Inputs from rivers and volcanic activity, removals by reactions with seafloor rocks and biological processes, mixing by currents, and the simple physical process of water evaporation. This balance has been relatively stable for hundreds of millions of years, allowing marine life to evolve and flourish in a chemical environment that, while not unchanging, varies only within certain limits. Imagine the ocean as an enormous mixing bowl, constantly being stirred by currents and tides. Rivers add fresh ingredients from the continents, dissolved minerals from weathered rocks. Volcanic vents inject heated, mineral-rich fluids from below. Evaporation removes pure water, leaving the dissolved material behind and concentrating it slightly. Chemical reactions at the seafloor remove some ions and add others. Biology extracts certain elements and redistributes others. And through it all, the water itself circulates, ensuring that over long periods, No part of the ocean remains isolated. Every part eventually mixes with every other part. This is the chemistry of salt water. Complex, dynamic, yet stable enough that marine organisms can depend on it. The taste of the sea comes from this particular balance of ions, this specific chemical signature that has characterized Earth's oceans for eons. And understanding this chemistry helps us understand not just why the ocean is salty, but why it has this specific saltiness, this particular flavor that any seagoer would recognize. Chapter 7. Volcanic Gifts from Below. Rivers are not the only source of salt in the sea. The ocean floor itself contributes minerals, and the mechanisms by which it does so are among the most dramatic and fascinating processes in all of Earth science. We must descend now to the deepest parts of the ocean, to volcanic ridges and hydrothermal vents, where seawater meets molten rock and emerges transformed. Deep beneath the ocean's surface, far from sunlight and the turbulence of surface waves, the seafloor is not flat and featureless. It is crossed by vast mountain ranges called mid-ocean ridges, volcanic systems that encircle the globe like seams on a baseball. At these ridges, tectonic plates diverge, and new oceanic crust is continually being created as magma rises from Earth's mantle and solidifies. This process, seafloor spreading, has profound implications for ocean chemistry. The newly formed volcanic rock is hot, often exceeding 400 degrees Celsius. It's also fractured and porous, riddled with cracks that allow seawater to penetrate deep into the crust. When cold seawater encounters hot rock, chemical reactions occur that fundamentally alter both the water and the rock. Seawater seeping into these cracks is heated as it descends. The heating is intense, reaching temperatures of 300 to 400 degrees Celsius in some systems. At these temperatures, water behaves differently than the cool liquid we're familiar with. It becomes more acidic, more reactive, hungry for chemical exchanges with the minerals around it. As the heated seawater passes through the hot basaltic rock, several things happen. Magnesium and sulfate ions, abundant in normal seawater, are removed through chemical reactions. The water donates these ions to the rock, where they become incorporated into new mineral structures. At the same time, the rock releases other ions into the water: iron, manganese, copper, zinc, silica, hydrogen sulfide. The water also picks up heat, enormous amounts of heat. This heated, chemically altered water is now less dense than the cold seawater surrounding it. Despite its new mineral load, buoyancy drives it upward. It rises through the fractured rock, accelerating as it heats further and pressure decreases. Finally, it erupts back into the ocean at hydrothermal vents. These vents are extraordinary features. Some emit fluids at temperatures exceeding 350 degrees Celsius, hot enough to melt lead, yet this water doesn't boil because the immense pressure at depth raises the boiling point. The fluid is typically black or dark gray, clouded with precipitating minerals. These are called black smokers because they resemble chimneys pouring smoke into the water, though what appears to be smoke is actually fine particles of metal sulfides forming instantly as the hot fluid mixes with cold seawater. Other vents emit cooler fluids, around 100 to 200 degrees Celsius. These may appear as shimmering water, the temperature difference causing visible distortion like a mirage. Some vents build mineral structures around themselves, chimneys that can grow to tens of meters tall, made of layered deposits of metal sulfides and other minerals precipitated from the vent fluids. The discovery of hydrothermal vents in the late 1970s revolutionized our understanding of ocean chemistry and biology. Scientists had long known that seawater chemistry implied some removal and addition of ions beyond what rivers could account for, but the mechanisms were unclear until these seafloor systems were actually observed. Hydrothermal circulation at mid-ocean ridges processes an enormous volume of seawater. Current estimates suggest that the entire volume of the ocean passes through these systems approximately every million years or so. This may sound like a long time, but it means that over geological history, seawater has been cycled through hydrothermal systems thousands of times. Each passage alters the water chemistry slightly. The cumulative effect is significant. Consider what hydrothermal systems do to ocean chemistry. They remove magnesium and sulfate from seawater, two of the most abundant ions. Without this removal, magnesium concentrations would be much higher than they are. They add iron, manganese, and other metals. Some of these metals precipitate quickly, forming deposits on the seafloor. Others disperse into the ocean, where they become nutrients for phytoplankton. Iron, for instance, is essential for photosynthesis, but scarce in many parts of the ocean. Hydrothermal input is one of the few sources for this critical element. Hydrothermal systems also add silica to seawater. This silica contributes to the pool that diatoms draw upon for their shells. They add hydrogen sulfide, which feeds unique ecosystems of bacteria that live near the vents, using the chemical energy in sulfides rather than sunlight to power their metabolism. The minerals deposited around hydrothermal vents are themselves fascinating. Rich in copper, zinc, and other metals, these deposits can be substantial. Some ancient hydrothermal deposits, now exposed on land due to tectonic uplift, are mined as valuable ore bodies. The process that creates these deposits has been operating for billions of years, cycling metals between the ocean and the crust. Beyond mid-ocean ridges, other forms of volcanic activity also contribute to ocean chemistry. Submarine volcanoes, unrelated to spreading ridges, erupt into the ocean, releasing gases and minerals. Volcanic islands form through this process. Iceland, Hawaii, the islands of the Pacific, all are volcanic in origin, and their activity adds substances to the surrounding seawater. Volcanic eruptions release gases that dissolve in seawater. Carbon dioxide is one, contributing to the ocean's inventory of dissolved carbon. Hydrogen chloride is another. Indeed, volcanic degassing may have been the original source of much of the chloride now dissolved in the ocean. When Earth was young and volcanic activity far more intense, massive amounts of chloride were released from the planet's interior and dissolved in the forming oceans. You might imagine the ocean floor as a vast chemical factory, operating continuously, powered by Earth's internal heat. Along thousands of kilometers of mid-ocean ridges, at hundreds of volcanic sites, seawater circulates through hot rock, exchanges ions, and emerges transformed. This has been happening since plate tectonics began, possibly as far back as 3 billion years ago. The ocean, as we know it, has been shaped as much by this submarine chemistry as by the rivers delivering dissolved minerals from the continents. The balance between what rivers add and what seafloor processes remove is crucial. If rivers added sodium and chloride to the ocean with nothing removing them, the ocean would become saltier over time. It would have been steadily increasing in salinity throughout Earth's history. but we don't see evidence for this. The ocean's salinity appears to have been relatively stable for at least the past 100 million years, probably much longer. Hydrothermal systems help maintain this balance. While they don't remove sodium and chloride directly in large amounts, they alter the overall chemistry in ways that affect other removal processes. They participate in the grand equilibrium that keeps ocean chemistry within the range we observe. There's something profound in realizing that the salt water we swim in, the ocean that covers most of Earth, has been chemically processed through volcanic systems in the deepest, darkest parts of the sea. The water has been heated to temperatures that would instantly scald us, has reacted with rock in near total darkness, has been transformed and returned to the ocean, carrying the deep Earth's chemical signature. Life has even found a way to thrive at hydrothermal vents, despite conditions that would seem utterly hostile. Unique bacteria convert chemical energy from hydrogen sulfide into organic matter, forming the base of a food chain that includes giant tube worms, unusual clams and mussels, and other organisms found nowhere else. These ecosystems exist in complete independence from sunlight, powered instead by the Earth's internal heat and the chemistry of mineral-rich vent fluids. The discovery of these ecosystems raised profound questions about the origins of life itself. Could life have begun in such an environment where chemical energy is abundant and organic molecules could form through reactions between hydrothermal fluids and seawater? We don't know for certain, but it's a possibility that many scientists take seriously. If so, the ocean's salt and the processes that create it might be intimately connected to the very origin of life on Earth. Let your mind descend into darkness, into the cold depths of the ocean floor, where vents glow with heat, where mineral-laden water billows upward in dark clouds, where chemistry and geology merge in a process that has shaped our planet for billions of years. The salt in the sea has sources both high and low, both from the weathering of mountains under open sky and from the reaction of water with hot rock in utter darkness. Together, these processes create the chemical environment that makes Earth's ocean unique. Chapter 8. Why salt stays while water leaves. The water cycle is one of the most fundamental processes on Earth. Intimately familiar, yet worth contemplating deeply. Water evaporates from the ocean, rises into the atmosphere, condenses into clouds, falls as rain or snow, flows across land, and returns to the ocean. This cycle has continued, without pause, for billions of years, and it's essential to understanding why the ocean is salty. Here's the crucial fact. When water evaporates from the ocean, it leaves the salt behind. Every dissolved ion, sodium, chloride, magnesium, all of them, remains in the liquid water. Only the water molecules themselves escape into the atmosphere as vapor. This is nature's distillation process, operating continuously at a scale beyond human comprehension. The ocean's surface is constantly evaporating. The sun's energy provides the heat needed to convert liquid water into vapor. Wind carries this vapor away, making room for more evaporation. In tropical regions, where the sun is intense and winds are steady, evaporation rates can exceed 2 meters per year, meaning a column of water 2 meters deep evaporates annually from each square meter of ocean surface. Even in cooler regions, evaporation continues, though at lower rates. The total amount of water evaporating from the ocean each year is approximately 400,000 cubic kilometers. This is an almost incomprehensible volume, enough to cover all of Earth's land surface to a depth of about 80 centimeters if it were spread evenly. Every year, this evaporation is balanced by precipitation falling back on the ocean and runoff from rivers. But the important point is the scale. Vast amounts of water are constantly moving from ocean to atmosphere, and every water molecule that evaporates leaves behind whatever was dissolved in the water it was part of. If you start with a cubic meter of seawater containing about 35 kilograms of dissolved salts and evaporate away the water, those 35 kilograms remain. If you evaporate half the water, the remaining water is twice as concentrated. Evaporate 90% of the water, and what's left is 10 times more concentrated. This concentration effect is why enclosed seas with high evaporation can become much saltier than the open ocean. The Mediterranean Sea is a good example. Evaporation exceeds the combined input from precipitation and rivers. Water flows in from the Atlantic through the Strait of Gibraltar, but much of this incoming water evaporates, leaving its salt behind. The Mediterranean's salinity is consequently higher than the Atlantic's. The Dead Sea provides an even more extreme example. It sits in a desert, receives limited river inflow, has no outlet, and experiences intense evaporation. Salt has been concentrating there for thousands of years. Its salinity is now about 340 parts per thousand, nearly 10 times saltier than the ocean. The water is so dense that you float effortlessly on the surface. The concentration of minerals is so high that few organisms can survive in it. Hence the name. If the ocean were a closed basin like the Dead Sea, it too would gradually become saltier as evaporation concentrated the dissolved ions. But the ocean is not closed. It's part of the global water cycle. Water that evaporates from the ocean falls as rain elsewhere. On land, in particular, that rain becomes rivers, and rivers return water to the ocean. The water completes a circuit. But the dissolved ions in the ocean don't complete this circuit. They remain behind when water evaporates. They don't travel with rain to the continents. They don't flow back in rivers. From the ocean's perspective, evaporation removes pure water, and rivers return water, plus additional dissolved minerals weathered from the land. The system has a one-way flow for salt, from land to sea, accumulating, with no equivalent return path. This raises an important question. If salt is constantly being added to the ocean by rivers and nothing is removing it, why isn't the ocean becoming saltier over time? Why hasn't it become a saturated brine over billions of years? The answer, which we'll explore more fully in the next chapter, is that removal processes do exist. They're not as obvious as evaporation and rivers, but they're sufficient to balance the input. The ocean has reached a chemical equilibrium where the rate of salt addition approximately equals the rate of salt removal. But for now, let's appreciate the role of the water cycle in maintaining the ocean's high salt concentration. Consider the selectivity of evaporation. It takes only water, leaving everything else. This property makes evaporation useful for purifying water. Solar stills, used to produce fresh water from seawater, rely on this principle. Evaporate the seawater, collect the vapor, condense it, and you have pure water with all the salt left behind in the residue. Nature has been running this solar still at global scale for eons. The ocean's surface is the evaporating basin. The atmosphere is the chamber where vapor rises and eventually condenses. Precipitation returns the purified water to the surface. But unlike a conventional still where you discard the concentrated brine, in the ocean, the brine is the ocean itself, and the purified water falls elsewhere, on land and in regions of high precipitation at sea, creating variations in salinity. The distribution of evaporation and precipitation across the ocean creates interesting patterns. In the subtropics, where evaporation exceeds precipitation, surface water becomes saltier. This salty surface water is also warmer, which normally would make it lighter, but the excess salinity makes it denser. Sometimes this water becomes dense enough to sink, carrying high salinity water into the ocean's interior. The Mediterranean outflow is an example. Very salty water flows out of the Mediterranean at depth, descending as it enters the Atlantic because it's denser than normal Atlantic water. In tropical convergence zones and at high latitudes, precipitation exceeds evaporation. Surface water here is fresher, less salty. When sea ice forms in polar regions, it also leaves salt behind. Ice is pure, frozen water, so the surrounding seawater becomes saltier. This salinity increase, combined with cold temperatures, makes polar surface water very dense. It sinks to form the deep water masses that fill the ocean basins, water that won't return to the surface for centuries. These patterns of evaporation and precipitation drive part of the ocean's circulation. Differences in temperature and salinity create differences in density, and density differences drive currents. This thermohaline circulation, literally temperature salt circulation, is a global conveyor belt that moves water masses from surface to deep and back again. It connects all ocean basins, ensuring that even the deepest water is part of a dynamic system. The water cycle itself varies over geological time. During ice ages, enormous amounts of water are locked up in continental ice sheets. Sea level drops by over 100 meters. The ocean becomes slightly saltier because the same amount of dissolved salt is contained in less water. When ice ages end and the glaciers melt, sea level rises and salinity decreases slightly. These are small changes in the scheme of things, a few percent, but they demonstrate that even over long periods, the water cycle influences ocean salinity. You might imagine a water molecule's journey. It sits at the ocean surface, part of the top millimeter where air and water meet. Sun warms it, winds evaporate it, and suddenly it's vapor, rising into the atmosphere. It travels with air currents, perhaps across thousands of kilometers. It condenses around a particle of dust, becomes part of a cloud droplet, merges with other droplets, grows heavy, and falls as rain. Maybe it falls on a mountain. It flows into a stream, picking up dissolved minerals. It travels down the river system, days or weeks in transit. Finally, it enters the ocean again, delivering its small cargo of ions, and the cycle can repeat. From the ion's perspective, the journey is different. A sodium ion in the ocean may have arrived yesterday via a river, or 1,000,000 years ago. It drifts with currents, sometimes near the surface, sometimes in the deep. It never leaves the ocean by evaporation. It will remain dissolved until some process removes it. Incorporation into sediment, chemical reaction with rock, biological uptake, and burial. These removal processes are slow, so the average sodium ion stays in the ocean for tens of millions of years. This asymmetry, water cycling rapidly, ions accumulating slowly, is fundamental to ocean chemistry. The water is transient, the salt is persistent. The ocean's volume varies with ice ages, but the total amount of dissolved salt remains relatively constant over much shorter timescales. This stability provides a consistent chemical environment for marine life. Let your thoughts drift like water vapor rising from the ocean surface, transforming, moving through cycles, but always returning. The ocean breathes water out into the atmosphere and receives it back again through rain and rivers, while the salt remains, patient, accumulated over deep time, a chemical memory of billions of years of weathering and volcanic activity. We've explored how salt enters the ocean, through rivers carrying dissolved minerals from weathered rocks, through volcanic activity at mid-ocean ridges and submarine volcanoes. We've seen how evaporation concentrates salt by removing pure water. But if salt only accumulated, never leaving, the ocean should be far saltier than it is after billions of years of Earth history. The ocean has reached an equilibrium, a balance point where salt addition equals salt removal. Understanding this balance is crucial to understanding modern ocean chemistry. The concept of residence time helps us think about this balance. Residence time is the average length of time a particular ion stays in the ocean before being removed by some process. Different ions have vastly different residence times. Sodium has a residence time of about 50 to 80 million years. Chloride is similar. These long residence times mean that once these ions enter the ocean, they remain there for geological ages before being removed. Other ions have much shorter residence times. Aluminum's residence time is only about 100 years. Iron's is even shorter, just a few hundred years. Silicon's residence time is about 10,000 years. These elements are removed from seawater much more rapidly than they're added, either by incorporation into biological structures, reaction with particles settling through the water, or chemical reactions at the seafloor. The residence time determines how an ion responds to changes in input or removal rates. Ions with short residence times quickly adjust to new conditions. Ions with long residence times, like sodium and chloride, respond very slowly. This is why sodium and chloride dominate seawater chemistry. They accumulate over long periods because removal is slow, even though their input rate from rivers isn't particularly fast. Several processes remove ions from seawater, maintaining the balance that keeps salinity relatively stable. One major removal mechanism is the incorporation of ions into sedimentary rocks. When ions react with clay minerals or other particles in seawater, they can become bound to the solid phase. As these particles settle to the seafloor and are buried by more sediment, the ions are effectively removed from the ocean. Hydrothermal circulation, which we discussed earlier, removes magnesium and sulfate from seawater through reactions with hot basaltic rock. This removal is significant enough that without it, magnesium concentrations would be much higher than they are. The removal occurs continuously at spreading ridges worldwide, processing vast volumes of seawater over geological time. Another important removal mechanism is the formation of evaporite deposits. In enclosed basins where evaporation is intense, seawater can become so concentrated that minerals precipitate out. The first mineral to form is usually calcium carbonate, limestone. As concentration increases further, gypsum, calcium sulfate, precipitates. With even more concentration, halite, sodium chloride, forms. Finally, in the most concentrated brines, potassium and magnesium salts precipitate. These evaporite deposits represent salt removed from the ocean. When the basin eventually becomes buried and isolated from the ocean, those salts are permanently removed from circulation. Over Earth's history, enormous volumes of evaporite deposits have formed. Some ancient deposits are now mined for salt and other minerals. Others remain buried deep in sedimentary basins. The interesting thing is that evaporite formation is sporadic and depends on specific conditions: an enclosed or semi-enclosed basin, a climate with high evaporation, and a connection to the ocean that allows water inflow while the basin becomes progressively saltier. These conditions don't always exist. During some geological periods, extensive evaporite formation has occurred. During others, it's been minimal. This variation affects ocean salinity over very long timescales, millions to tens of millions of years. Biological processes also remove ions from seawater. Marine organisms extract calcium and carbonate to build shells and skeletons. The amount of calcium carbonate produced by marine life is enormous. Billions of tons per year. Coccolithophores, tiny planktonic algae, coat themselves in microscopic calcite plates. Foraminifera, single-celled organisms, build intricate calcium carbonate shells. Corals construct vast reefs. Mollusks grow shells. When these organisms die, their hard parts sink. In shallow and moderate depths, calcium carbonate accumulates on the seafloor. Over time, it lithifies into limestone. Limestone is one of the most abundant sedimentary rocks on Earth, and it represents calcium removed from seawater. The famous White Cliffs of Dover in England are made of chalk, which is simply very pure, fine-grained limestone composed of countless tiny shells. In the deepest parts of the ocean, below about 4 to 5 kilometers depth, calcium carbonate dissolves rather than accumulating. The pressure is high, temperature is low, and these conditions make seawater slightly undersaturated with respect to calcium carbonate. Shells dissolving at depth return calcium and carbonate to seawater. This creates a balance. Shallow and moderate depth regions bury calcium carbonate, removing it from the ocean. The deepest regions dissolve it, returning it. Diatoms remove silicon from seawater to build their glass-like shells called frustules. When diatoms die and sink, their frustules accumulate on the seafloor. In some regions, especially in productive areas like the Southern Ocean and the Equatorial Pacific, thick deposits of diatom shells build up. These eventually become rocks, called cherts. This process removes dissolved silicon from seawater, balancing the input from rivers. Subduction zones, places where tectonic plates converge and oceanic crust descends into the mantle, also play a role in salt removal. Sediments on the descending plate can carry water and dissolved ions into the mantle. Some of this material is released by volcanic activity at the subduction zone, returning to the surface, but some descends permanently into the deep earth, effectively removing it from the ocean atmosphere system for geological ages. The balance between addition and removal processes has maintained ocean salinity within a fairly narrow range for at least the past several 100 million years. We have good evidence for this from marine sediments and from the fossil record. Organisms that live in the ocean today are adapted to a specific salinity range. Fossil organisms from hundreds of millions of years ago appear similar to their modern relatives, suggesting they lived in water with similar chemistry. However, over longer timescales, billions of years, ocean salinity likely has varied more significantly. The very early ocean, when volcanic activity was more intense and the continents were smaller and less weathered, probably had different chemistry than today's ocean. As continents grew and weathering patterns changed, ocean chemistry evolved. The rise of life itself altered ocean chemistry, particularly after photosynthetic organisms began producing oxygen and removing carbon dioxide. It's remarkable that this balance exists at all. There's no conscious regulation, no controlling intelligence. It's purely the result of physical, chemical, and biological processes operating according to natural laws. Yet these processes have maintained ocean salinity within bounds that allow life to thrive for hundreds of millions of years. In a sense, the ocean's chemistry is self-regulating through feedback loops. For instance, if rivers were to suddenly deliver more calcium to the ocean, the concentration of calcium in seawater would begin to rise. This would make seawater more supersaturated with respect to calcium carbonate. Marine organisms would find it slightly easier to build shells. More calcium carbonate would precipitate chemically in warm, shallow waters. These processes would remove the excess calcium, returning the ocean to equilibrium. The system has negative feedback. Perturbations tend to be corrected over time. Similarly, if volcanic activity increased, adding more dissolved minerals to the ocean, various removal processes would accelerate. More sediment formation, more evaporite deposition, more rapid hydrothermal circulation, all would work to remove the excess. The equilibrium would shift slightly, but the ocean wouldn't undergo a radical change in chemistry unless the perturbation were truly enormous and sustained. This stability is what has allowed complex marine ecosystems to evolve and persist. If ocean chemistry were wildly variable on short timescales, organisms couldn't adapt. They need a predictable chemical environment to regulate their internal chemistry, to build shells, to reproduce, to survive. The ocean provides this, not through design but through the natural balance of geological and biological processes. As you rest and contemplate this balance, consider how intricate and yet how robust it is. Countless processes, operating at scales from molecular to global, from time scales of seconds to millions of years, all contributing to the stable chemistry of seawater. The ocean is salty, but not too salty. It's been this way for eons, and it will likely remain so for eons to come, barring catastrophic changes to Earth's climate or geology. This stability is a gift of planetary chemistry, a consequence of Earth's dynamic geology and the properties of water itself. Chapter 10: Seas of Different Saltiness. While the open ocean maintains a relatively uniform salinity of about 35 parts per thousand, not all bodies of salt water share this characteristic. Earth hosts a variety of seas, gulfs, and lakes with drastically different salinities, each telling a story about local climate, geology, and hydrology. Exploring these variations helps deepen our understanding of the processes that control salt concentration in water. The Baltic Sea, in northern Europe, is one of the least salty seas connected to the ocean. Its salinity ranges from about 7 parts per thousand in the far north to about 15 parts per thousand near its connection to the North Sea. The Baltic is relatively fresh because it receives substantial runoff from rivers draining a large area of northern Europe, and it has only a narrow, shallow connection to the saltier ocean. Precipitation exceeds evaporation in this region, further diluting the water. Marine organisms adapted to normal ocean salinity cannot survive in the Baltic, and freshwater organisms find it too salty. The result is a unique ecosystem with species specially adapted to these brackish conditions. The Mediterranean Sea presents the opposite situation. Its salinity averages about 38 to 39 parts per thousand, noticeably higher than the Atlantic. The Mediterranean lies in a region where evaporation significantly exceeds precipitation and river input. Water flows in from the Atlantic through the Strait of Gibraltar at the surface, and denser, saltier water flows out at depth. This exchange maintains the connection, but the net effect is that the Mediterranean concentrates salt through evaporation. In ancient times, about 6 million years ago, the Strait of Gibraltar closed, and the Mediterranean largely dried up, leaving vast salt deposits. When the strait reopened, the ocean refilled the basin, redissolving some of those salts and re-establishing the sea. The Red Sea is even saltier, with salinities around 40 to 41 parts per thousand in its central and northern regions. It sits in a hot, dry climate where evaporation is intense and rainfall minimal. The Red Sea receives limited river inflow and has only a narrow connection to the Indian Ocean through the Strait of Bab el-Mandeb. Like the Mediterranean, it loses water by evaporation faster than it's replenished by precipitation and runoff, causing salt to concentrate. Perhaps the most extreme example of salt concentration is the Dead Sea, though technically it's a lake rather than a sea. Its salinity approaches 340 parts per thousand, nearly 10 times the ocean's salinity. The Dead Sea sits at the lowest point on Earth's land surface, about 400 meters below sea level, in the Jordan Rift Valley. It receives inflow from the Jordan River and a few smaller streams, but it has no outlet. Water leaves only by evaporation, which is extremely high in the hot, dry climate. Salt has been concentrating for thousands of years. The Dead Sea is so salty that its water feels oily to the touch. You float effortlessly because the density is so high, about 1.24 grams per cubic centimeter, compared to seawater's 1.025 and freshwater's 1. Swimming is nearly impossible because your body sits so high in the water. The high salinity also affects the water's properties. It freezes at about -6 degrees Celsius instead of 0, and its boiling point is elevated. Few organisms can survive in water this salty. Those that do are mostly bacteria and archaea specifically adapted to extreme salinity. The Great Salt Lake in Utah offers another example of an extremely salty closed basin. Its salinity varies depending on water level, which itself varies with precipitation and runoff. It has reached salinities over 270 parts per thousand during dry periods. Like the Dead Sea, the Great Salt Lake has no outlet, and evaporation exceeds input, causing salt concentration over time. On the other end of the spectrum, some lakes are much fresher than seawater despite being called seas. The Caspian Sea, the world's largest lake, has salinity of only about 12 parts per thousand. It's landlocked and fed by rivers, especially the Volga. Because it sits in a region where precipitation and runoff are sufficient, and because it's enormous, the concentration effect of evaporation is less dramatic than in smaller closed basins. These variations in salinity demonstrate how local conditions can override global averages. Climate determines the balance between evaporation and precipitation. Geology determines whether a water body has outflows or is closed. Hydrology determines river inflow. The size of a water body matters too. Larger bodies mix better, and are less affected by local perturbations. Within the open ocean itself, salinity varies with latitude and depth. Surface salinity is highest in subtropical regions, around 20 to 30 degrees north and south of the equator. Here, dry air descends, skies are often clear, evaporation is high, and precipitation is low. These are the regions of subtropical deserts on land: the Sahara, the Arabian Desert, the Australian outback. Over the ocean, the same climatic conditions create elevated salinity. Near the equator, salinity is lower. The intertropical convergence zone brings abundant rainfall. Evaporation remains high because temperatures are warm, but precipitation exceeds it, creating a net input of fresh water that dilutes surface salinity. You can see this pattern clearly on maps of ocean salinity. A belt of lower salinity near the equator, flanked by belts of higher salinity in the subtropics. At high latitudes, salinity is again lower. Precipitation exceeds evaporation, and melting sea ice contributes fresh water. Polar surface water tends to be cold and relatively fresh. Though it's low, temperature makes it dense despite the lower salinity. This dense water sinks to form the deep water masses of the ocean. Seasonal variations in salinity also occur. Regions with pronounced rainy and dry seasons see salinity decrease during the wet season and increase during the dry season. River inflow varies seasonally too, affecting coastal salinity patterns. Near the mouths of major rivers, salinity can change dramatically over short distances as fresh water mixes with seawater. Estuaries, the regions where rivers meet the ocean, display complex salinity patterns. Fresh water is less dense than salt water and tends to flow out over the top of a wedge of salt water, intruding upstream. The boundary between these water masses is called the halocline, the zone of rapidly changing salinity. This stratification affects circulation, with surface water flowing seaward and deep water flowing landward. Tidal cycles complicate the pattern further, pushing salt water farther upstream during high tide and allowing it to retreat during low tide. Some organisms are adapted to these varying salinity environments. Salmon begin life in fresh water, migrate to the ocean, where they spend years in full-strength seawater, then return to fresh water to spawn. They must be able to regulate their internal chemistry across this enormous range. Marine organisms that colonize estuaries often have wide salinity tolerances. Purely freshwater or purely marine organisms cannot survive in these transitional zones. Coral reefs provide another example of salinity sensitivity. Most reef-building corals require relatively stable salinity, close to normal seawater values. Heavy rainfall that significantly freshens surface water can stress or kill corals. Conversely, extremely high salinity from intense evaporation in shallow lagoons can also be problematic. Healthy reefs grow in regions where salinity remains within a narrow range. The variations in salinity across Earth's water bodies remind us that the ocean's average value of 35 parts per thousand is not inevitable or universal. It's the result of global scale balances between processes, adding and removing salt, and between evaporation and precipitation. Change any of these factors significantly. Alter the climate, close or open connections between seas, change river inflow patterns, and salinity will shift. Over geological history, major changes in ocean salinity have likely occurred. During periods of intense evaporite formation, when many enclosed basins were precipitating salt, average ocean salinity may have decreased slightly. as salt was removed from circulation. When these basins later reconnected to the ocean and the evaporites dissolved again, salinity would have increased. Ice age cycles also affect salinity. During glacial maxima, when sea level is low, the ocean is slightly saltier. During interglacials, when ice melts, it's slightly fresher. Yet, through all these variations, ocean salinity has remained within bounds that life can tolerate. It hasn't become saturated brine, nor has it become fresh water. The mechanisms of balance, weathering, volcanic input, biological removal, chemical precipitation, have maintained ocean chemistry in a life-supporting range for hundreds of millions of years. This stability, despite variations at local and regional scales, is one of the remarkable features of our planet. Let your mind drift across these different waters, from the nearly fresh Baltic to the incredibly salty Dead Sea, from tropical rain-freshened seas to evaporation-concentrated gulfs. Each body of water tells a story about climate and geology, about balance and imbalance, about the factors that make water salty or keep it fresh. The ocean's 35 parts per thousand is one point in a spectrum, a balance point maintained by planetary processes operating at every scale. Chapter 11. Life in Salt Water. Life evolved in the ocean. In salty water, every organism alive today, whether it lives in the sea, on land, or in fresh water, carries in its cells the chemical signature of marine ancestry. Understanding how organisms cope with the ocean's saltiness illuminates not just marine biology, but the fundamental nature of life itself. The challenge salt water poses is osmotic. Living cells contain water with dissolved ions, proteins, and other molecules. If a cell is placed in pure water, water will flow into the cell by osmosis, trying to equalize concentrations. The cell may swell and burst. Conversely, if a cell is placed in very salty water, water will flow out of the cell, and the cell will shrink and lose function. Organisms living in the ocean must somehow maintain their internal chemistry in the face of the surrounding salt water. Marine organisms have evolved three basic strategies to deal with this challenge. Some maintain their internal salinity at approximately the same level as seawater. They're called osmoconformers. Others maintain internal salinity different from seawater. These are osmoregulators. And some organisms use organic compounds, rather than salts, to balance osmotic pressure, reducing the problem of high ion concentrations in their cells. Most marine invertebrates are osmoconformers. Their body fluids have the same salt concentration as the surrounding seawater. When salinity changes, their internal chemistry changes in parallel. This strategy requires minimal energy, no pumping of ions against concentration gradients, no complex regulation. It works well as long as salinity doesn't vary too dramatically or too rapidly. Jellyfish, sea stars, sea urchins, many crustaceans. These animals are essentially small packets of seawater with specialized structures for feeding, moving, and reproducing. Marine fish, however, are osmoregulators. They maintain internal salt concentrations lower than seawater. A marine fish's blood has a salinity of about 12 parts per thousand, less than half the concentration of the surrounding ocean. This creates a constant osmotic challenge. Water tends to flow out of the fish's body into the saltier environment. Salt tends to flow in. The fish must counteract both tendencies. Marine fish handle this by drinking seawater continuously. The water passes through their digestive system, where most of the salt is excluded while water is absorbed. The salt that does enter the blood is actively pumped out through specialized cells in the gills. These gill cells use energy to move ions against their concentration gradient, from low concentration in the blood to high concentration in the surrounding water. The fish also produces very little urine, conserving water. It's an energetically expensive strategy, but it allows the fish to maintain stable internal chemistry. Sharks and rays use a different approach. They retain urea, a nitrogen-containing waste product that most animals excrete, in their blood. This raises the osmotic concentration of their blood to nearly match seawater, but without accumulating high concentrations of salt ions. The high urea would normally damage proteins and cell membranes, but sharks and rays also accumulate trimethylamine oxide, an organic compound that counteracts urea's negative effects. This strategy allows them to be nearly in osmotic equilibrium with seawater, while keeping salt concentrations in their cells relatively low. Marine mammals and seabirds face similar challenges. They're descended from land animals and thus maintain internal salt concentrations much lower than seawater. They cannot drink seawater without becoming dehydrated because their kidneys cannot produce urine more concentrated than their blood. If they drink seawater, they must urinate out all the salt, but this requires more water than they gained by drinking. They would suffer net water loss. Marine mammals get most of their water from their food, fish and squid. Their primary prey contain water that's less salty than seawater. Metabolizing fat also produces water. Seabirds have an additional adaptation: salt glands, usually located near the eyes, that can secrete a concentrated salt solution, allowing them to excrete excess salt without losing much water. A seabird can drink seawater, absorb the water, and excrete the salt through these glands, ending up with a net gain in water. The earliest life on Earth likely evolved in the ocean, possibly near hydrothermal vents or in tidal pools. These early organisms had to cope with seawater chemistry from the beginning. As life diversified, some lineages remained marine, others invaded fresh water and, eventually, land. Each transition required adaptations to new osmotic challenges. Freshwater organisms face the opposite problem from marine organisms. They're surrounded by water with very low salt concentration. Water tends to flow into their cells by osmosis. Freshwater fish must constantly pump out water, producing copious, dilute urine. They actively absorb salts from their food and from the water flowing over their gills, replacing what they lose in urine. It's energetically costly, just like marine osmoregulation, but it allows freshwater fish to maintain stable internal chemistry. Organisms that move between fresh and salt water face the greatest challenge. Salmon are famous for this. They spend their juvenile stage in fresh water, undergo physiological changes called smoltification that prepare them for seawater, migrate to the ocean where they spend years feeding and growing, then return to fresh water to spawn. During their life cycle, salmon must switch between excreting excess water in fresh water and conserving water in seawater. They adjust the number and function of specialized cells in their gills, changing from freshwater to marine ion pumps and back again. The ability to regulate salt balance is fundamental to life in water. Even single-celled organisms must manage ion concentrations. Many protists have contractile vacuoles, structures that collect excess water and pump it out of the cell. Without this mechanism, the cell would swell and burst in fresh water, or shrink and die in very salty water. The cells of all organisms maintain concentrations of specific ions that differ from their surroundings. Sodium is typically kept at low concentration inside cells, while potassium is kept at high concentration. This imbalance is maintained by ion pumps in cell membranes, molecular machines that use energy to move ions against their concentration gradients. These pumps are universal in life, operating in bacteria, plants, animals, fungi, every domain of life. The sodium-potassium pump alone consumes about a third of the energy used by typical human cells at rest. The internal salinity of most organisms' cells and body fluids is not identical to modern seawater, but it's not entirely different either. Human blood, for instance, has a salinity of about 9 parts per thousand, much less than seawater's 35, but still salty. The ratio of ions is also different. Blood has more potassium relative to sodium than seawater does. These differences reflect both evolutionary history and physiological necessity. Some scientists have speculated that the internal chemistry of organisms reflects the salinity of the ancient ocean when life first evolved or when particular lineages invaded land. If the early ocean was less salty than today's ocean, organisms evolving then would have internalized that chemistry, and their descendants would continue to maintain it even as ocean salinity increased. The evidence for this idea is ambiguous, and it remains debated. But it's an intriguing thought that the composition of our blood might be an echo of ancient seas. Marine plants face different challenges than animals. Seaweeds and marine phytoplankton must maintain their cell structure despite the osmotic pressure of surrounding salt water. Many use organic compounds, sugars, amino acids, and other molecules to balance osmotic pressure rather than relying solely on salt ions. This keeps the salt concentration in their cells moderate while still preventing water from flowing out. Coral reefs, among the most productive and diverse ecosystems on Earth, exist only in relatively stable, salty seawater. The symbiotic relationship between corals and their photosynthetic algae is sensitive to salinity changes. Significant freshening of water, such as from heavy rainfall or river flooding, can stress corals and cause bleaching. Similarly, excessive salinity from evaporation in shallow lagoons can be harmful. The thriving of coral reefs depends on the ocean's stable chemistry, including its salinity. Deep-sea organisms experience additional challenges. Pressure at depth affects biological molecules and membranes. Organisms living at great depths have adaptations to stabilize proteins and maintain membrane fluidity under high pressure. Some use special organic molecules that counteract pressure effects. The combination of cold temperature, high pressure, and normal seawater salinity creates a unique environment requiring specialized adaptations. Throughout life's history, the ocean's salinity has shaped evolution. It has selected for mechanisms of salt regulation, driven the development of osmoregulatory organs, and constrained which organisms can live where. Estuaries, with their variable salinity, are particularly stressful environments, and only organisms with flexible osmoregulatory abilities can thrive there. The open ocean, with its stable salinity, allows for more specialized adaptations. Life and seawater chemistry have co-evolved. Organisms affect ocean chemistry through their metabolism, extracting calcium, producing oxygen, consuming nutrients. Ocean chemistry affects organisms by setting the osmotic conditions they must cope with, by providing or limiting essential elements, and by creating the stable environment in which complex ecosystems can develop. As you contemplate life in saltwater, consider how thoroughly organisms are integrated with their environment. A fish is not separate from the ocean. It's engaged in constant chemical dialogue with the water surrounding it, actively managing ion concentrations, maintaining the boundary between inside and outside. Every cell in every marine organism performs this delicate balancing act, moment by moment, throughout its life. The ocean is salty, and life has learned not just to tolerate this, but to thrive within it, to use it, to depend on it. The salt that makes the ocean taste sharp and mineral is the same salt that flows through the veins of marine life, connecting all ocean dwellers in a shared chemistry of survival. Chapter 12. The Future Ocean. As we near the end of our journey tonight, let's turn our attention gently toward the future. The ocean's saltiness, which has been relatively stable for so long, is not immune to change. Climate shifts, human activities, and natural geological cycles all have the potential to alter ocean chemistry over time. Yet the ocean is resilient, vast, and buffered by powerful regulatory processes. Understanding both the vulnerabilities and the resilience helps us appreciate this remarkable system. Climate change is currently altering the global water cycle. Warmer air holds more moisture, which intensifies evaporation from the ocean and increases precipitation in many regions. But the distribution of these changes is uneven. Some regions are experiencing more rainfall, others more drought. This affects the balance of evaporation and precipitation that influences salinity patterns. In regions where precipitation increases, surface ocean salinity decreases slightly. In regions where evaporation increases more than precipitation, surface salinity rises. Scientists have observed these trends over recent decades. The subtropical regions with naturally high salinity are becoming slightly saltier. Regions near the poles and equator with naturally lower salinity are becoming slightly fresher. The pattern that existed is intensifying. Wet areas are getting wetter. Salty areas are getting saltier. Fresh areas are getting fresher. These changes don't dramatically affect the ocean's average salinity, which remains close to 35 parts per thousand, but they matter for ocean circulation. Salinity, along with temperature, determines water density. Changes in surface salinity affect where and how water masses sink from the surface to the deep ocean. They influence the thermohaline circulation, the global conveyor belt of ocean currents that redistributes heat and nutrients worldwide. Melting ice sheets also affect ocean salinity. Greenland and Antarctica are losing ice mass as climate warms. This fresh water flows into the ocean, diluting surface salinity in polar regions. The North Atlantic, in particular, is experiencing freshening as Greenland's ice melts. This could affect the Atlantic meridional overturning circulation, a major current system that includes the Gulf Stream. Some scientists are concerned that sufficient freshening could slow or even shut down this circulation, with significant climate consequences. However, the ocean is enormous, and changes in salinity take time to spread. The deep ocean remains largely unaffected by surface changes in the short term. The ocean's volume is so vast, about 1.3 billion cubic kilometers, that even large inputs of fresh water have limited immediate impact on average salinity. Melting all of Greenland's ice would lower average ocean salinity by only about 1 part per thousand. Melting both Greenland and Antarctica would lower it by about 3 parts per thousand. Significant, but not catastrophic for ocean chemistry. River flow patterns are also changing. Some rivers are carrying more water due to increased precipitation in their drainage basins. Others are sumpent, diminishing due to drought, water extraction for human use, or changes in snowmelt timing. These changes affect the delivery of dissolved minerals to the ocean, though again, the effects are gradual, and the ocean's enormous volume buffers against rapid change. Human activities directly affect some enclosed seas. The Dead Sea is shrinking because water is diverted from the Jordan River for irrigation and drinking water. As the Dead Sea shrinks, its salinity increases even further. What was already an extreme environment is becoming more extreme. Similar issues affect the Aral Sea in Central Asia, which has lost much of its volume due to water diversion, becoming far saltier than it originally was. Ocean acidification, though not directly related to salinity, is another change affecting ocean chemistry. As atmospheric carbon dioxide increases, more dissolves in seawater, forming carbonic acid. This lowers the ocean's pH, making it more acidic. Ocean pH has decreased by about 0.1 units since pre-industrial times. This affects marine organisms, particularly those that build shells or skeletons from calcium carbonate, because lower pH makes it harder to form these structures. Coral reefs are especially vulnerable. The combination of changing salinity patterns, warming temperatures, and acidification represents a suite of chemical changes that the ocean hasn't experienced in millions of years, at least not at this pace. Marine ecosystems are adapting, but rapid change is stressful for organisms that evolved in stable conditions. Some species will migrate to new regions as conditions change. Others will struggle or decline. Yet the ocean has experienced far greater changes in the distant past and recovered. During the last ice age, sea level was 130 meters lower than today, and ocean salinity was noticeably higher. When the ice melted, salinity decreased. During even older periods, ocean chemistry was dramatically different. Different pH, different concentrations of various ions, different temperature distributions. Life persisted through these changes, though ecosystems were transformed and some species went extinct. The geological processes that maintain ocean salinity, weathering, volcanic activity, hydrothermal circulation, biological cycling, continue operating. Rivers still deliver dissolved minerals. Hydrothermal vents still process seawater through hot rock. Marine organisms still build shells and extract ions from seawater. These processes are slow by human standards, but they're inexorable on geological timescales. Over millions of years, the ocean's chemistry will continue to evolve. Continental drift changes weathering patterns as mountains rise and erode. Volcanic activity varies with tectonic cycles. Ice ages come and go, raising and lowering sea level, altering climate and weathering rates. Through all these changes, the fundamental processes that make the ocean salty persist. In a very long view, hundreds of millions of years into the future, Earth's ocean may change more dramatically. The sun is gradually brightening as it ages. Eventually, Earth will become so warm that the oceans evaporate away entirely. But this fate is billions of years distant, almost incomprehensibly far in the future. For any timescale relevant to humanity or even to most of Earth's future biosphere, the ocean will remain a salty sea, covering most of the planet, supporting life, cycling water, and minerals. There's something comforting in this continuity. The ocean that ancient fish swam in, the ocean that saw the first whales evolve, the ocean that human ancestors learned to navigate, it's fundamentally the same ocean we know today. Its salinity connects us to deep history, to the weathering of mountains that no longer exist, to volcanic eruptions that no one witnessed, to the patient accumulation of ions over billions of years. As you rest tonight, let your mind return to the beginning of our journey. We started with a simple question: why is the ocean salty? We've explored the answers through chemistry and geology, through the water cycle and biology, through timescales from seconds to eons. The ocean is salty because water dissolves rock, because rivers carry dissolved minerals to the sea, because volcanic activity adds ions from Earth's interior, because evaporation concentrates what remains, and because the system has reached a balance where addition and removal roughly equal each other. But the ocean's saltiness is more than just chemistry. It's a story of how Earth works, how water shapes the planet, how life adapts and thrives. The salt in the sea is a connection between land and ocean, between solid and liquid, between geology and biology. It's a reminder that Earth is a system, integrated and dynamic, where processes at every scale influence each other. The taste of seawater, sharp, mineral, unmistakable, is the taste of billions of years of planetary evolution. Every sodium ion, every chloride ion, every dissolved element has a history, a journey from rock to river to sea. Together, they make the ocean what it is, a salty solution that covers most of Earth, that moderates climate, that gave birth to life, and continues to sustain it. Let this knowledge settle over you like a calm sea. The ocean's saltiness, which might have seemed like a simple fact, reveals itself as a complex story when you look closely, a story still unfolding, still being written by rivers and rain, by volcanoes and life, by the slow, patient processes that shape our world. The ocean will be there tomorrow, salty as ever, waves rolling onto shores, tides rising and falling, currents circulating slowly through the deep. It will be there for all your tomorrows, faithful and vast, ancient and ever-renewing. Let this constancy comfort you. Let the rhythm of waves guide you toward rest. Thank you for joining me on this journey through science and wonder. May your sleep be peaceful, your dreams gentle, and your mind at ease. The ocean remembers everything, but you need remember nothing, only that you are part of this remarkable world where salt and water meet, where rock becomes sea, where chemistry becomes life. Sleep well, and let the ocean cradle you in its patient, salty embrace.